right, we're going to talk about taps today. What I have done in the past is have everybody go find the tap rules in the code book, but we're not going to do that today. As some of you know, I'm a member of the IEIA, IEIOU, or something like that. No, International Association of Electrical Inspectors, and at one of them, Joe Andre from National Electrical Manufacturers Association gave a great lecture on the tap rules, and I should have just recorded his, and that way you wouldn't have to hear mine, but I didn't, so you're going to have to. And he has, shall we say, retired, so you can't call him and ask him questions, but there's a new NEMA rep that can answer questions about tap rules because they're one of the major instigators of the tap rule code sections. Okay, we're going to talk about Article 240, overcurrent protection for conductors, 240.4, protection of conductors in general, power loss hazard, 800 amp or less, and tap conductors. Really and truly, we just want to talk about tap conductors. You know that the National Electrical Code is not a design manual. It is not a design manual. It is a minimum, that's easy for you to say, a minimum standard. And that's all it is. Okay? Good design for your system may necessitate values other than the minimum or maximum NEC values. In other words, once again, NECA or NEC is a minimum standard, and that is all. Sometimes you can build a much better system, mostly, usually. Okay, desired level short circuit protection, feeder and circuit operating characteristics, coordination, so on and so on, functionality. Okay. You all know what overcurrent is. We've been talking about that quite a bit. Any current in excess of the rated current of the equipment or the ampacity of a conductor. It may result from the overload, short circuit, or ground fault. Remember that overload always refers to a slight overcurrent condition that goes on and on because of some condition that's happening for a long time. The short circuit is literally a dead short, and it happens very quickly. The definition of a short circuit, remember, is a short between two energized conductors, and that includes a neutral conductor where it's an energized conductor. Okay, so a ground fault is a different classification also. It's still a short circuit, but it's where the short circuit goes from a hot conductor, an energized conductor, to anything except another energized conductor, including neutrals. It goes to the conduit, the grounding conductor, the conduit, the frame, a fence, dirt, water, anything except another energized conductor. That is a ground fault. And usually it'll be a fairly small current because the resistance will be fairly high. The minimum resistance for ground rods to the earth is about 25 ohms, but if you figure 25 ohms, that's enough resistance to load a circuit so that the amperage goes down, right? If you have a 120 volt circuit with 25 ohms, what is your total current? Okay, if it's 5 amps, are we sure about that, by the way? Around 5 amps. Okay, we'll go with that. If you've got a 15 or a 20 amp breaker and it's loaded at 5 amps, when is it going to turn the circuit off? Never. That's why ground faults are so dangerous. So ground faults are very dangerous. Short circuits are kind of dangerous for about less than a quarter of a wave. And a quarter of a wave is 1/4 of 1/60th. So 4 times 60, 120, 240. So a very big current can flow for about 240th of 1 second. And yes, it's going to be a big splash in the water, as it were, because we kind of identify water and electron movement kind of in the same thing. It's got to be like a big blurb of water flying out of a fire hose for just a split second, right? And that could probably do some damage, but nothing like that constant flow from a ground fault. Okay, so let's go to the next one. Oh, I did. Okay, and we're going to talk about, mainly we're going to talk about tap conductors. I think I went down. I think I went the wrong way. This out of the way. Okay. An overload, we know what an overload is. It's a constant flow where the flow is a little higher than it ought to be. If it's a motor, it's drawing more current than the wires inside the motor can actually stand for a long period of time. Ground fault, very, very, very dangerous, smaller current. Okay, short circuit impedance, short circuit current ratings, and other characteristics. Okay, in general, conductors must be protected against overcurrent in accordance with their ampacities. Ampacities are determined by 310.16 in the code book. Standard ampere ratings for overcurrent devices are found in 240.6. Those are two. Next week, we're going to talk about motor block. We're going to start talking about motor block a great deal. And we're going to mark several places in our code book, and I can guarantee you the 310.16 and 240.6 are going to be a couple of the pages you're going to tab. Okay? You can use the next higher standard device unless it exceeds 800 amps. And what if there's no standard overcurrent protection device for your conductor? Unless you can go to the next higher one, unless it exceeds 800 amps. And it's not used for branch circuits supplying more than one receptacle for cord and plug portable loads. What does that second one mean? It is not used. You can use the next higher standard device unless it is not used for branch circuit. In other words, it's saying you can if. Is that correct? You need to understand what this thing's saying. If there's no standard overcurrent protection for my conductor, you can use the next higher unless it is not used for a branch circuit supplying more than one receptacle for cord and plug portable loads. So what is it saying about one receptacle, cord and plug receptacle loads? Does that mean you can or cannot? Well, we'll look that up in the code book soon, like between now and next week. Okay, now a tap, I'm going to cut to the chase here. We're going to be talking about, remember we talked at the very beginning of the semester about one of the things you want to be able to do is you walk into a room and some owner comes over and says, I want this machine here, this one there, that one there, and I want this machine right over there. And I want you to get this all hooked up by tomorrow night, right? You need to sit down and write your material list, right? Okay, what you're going to be putting in is you're going to be putting in a run back to the main distribution panel to supply this whole load, right? So you're going to bring a supply circuit to the area, and you're going to go into an auxiliary gutter to make your connections to your 4, 5, 6, however many motors and pieces of equipment that are in the room that you're going to connect. And you're going to take a run from there to its safety switch, its disconnect, its EXO, electrical cutoff. And from there, you're going to go down to your motor starter. Well, the wires in between where you bring that supply branch circuit from the distribution panel to the auxiliary gutter down to the safety switch, EXO, whatever you want to call it, it's called a tap conductor, okay? And sizing that tap conductor is an unusual rule because you're not protecting it with a circuit breaker at the top end. That wire is being protected by the fuses that supply your equipment, your starter, and your motor, okay? That circuit is protecting. So because of that, the wire size is limited to a formula, and we're going to talk about that in a few minutes. Okay, the title of the section refers to the location of the overcurrent protection. It's generally required conductors be protected at their ampacity, where they receive their supply. In other words, it's normally at the top end of the circuit, right? Except for tap conductors. Where it's not possible, practical, or just not designed that way. Allowances are made for protection elsewhere in the circuit, like at the bottom end of the circuit. Okay. Remember, conductors need to be protected from short circuit, ground fault, and overload. And really and truly, our tap conductors, we only really need to, sorry, yeah, it's easy for you to say, only need to protect against short circuits. The ground fault, fuses and breakers are really not going to protect against a ground fault at all, are they? Unless they're GFCI receptacles or breakers. They're not going to be. In a motor situation, they're probably not going to be. And the overload is going to be protected in the motor overloads. So we're really talking about three different things here. The short circuit is protecting the conductors, period. Stop. Okay? I don't want you to get confused about these things at all. I want you to be very clear about these definitions. Short circuit, you're protecting the wires. Stop. That's it. That's all. Okay? Ground fault, you can't really protect against that in the motor situation, can you? And overload, that is not taken care of by, generally speaking, is not generally taken care of by the fuses or the circuit breakers that protect the branch circuit conductors. Okay, it's not being done there. It's being done by the motor starter and the overload block. Overload block. Okay. Short circuit and ground fault currents are generally quite high. A short circuit is going to be a very short, very high current blast. It's like if you have a fire hose and you have it capped off on the far end, but you've got that nice cloth hose, this 3-inch hose, and it straightens out in a rigid form because under fire hose is under what's the valve, the big red valve on the corners? Fire hydrant. It's under hydrant pressure, which is way higher than your street pressure. Way higher. Okay? Now, your garden hose is never under more than about 35 psi, but that fire hose might be under hundreds of pounds of pressure per square inch. And it's 3 square inches across, right? So there's lots of pressure in there. Now, what if you take a little tiny needle and you punch a hole in that fire hose? That water is going to come screaming out, and the water is going to make a bigger and bigger hole in almost said insulation, in the fire hose, right? Same deal with a short circuit. Okay, so once again, we can see there's a similarity between water and electrons. You punch a little tiny hole, you get a little tiny nick in the wire, and as it flows out, as it becomes a short circuit, it's going to make a bigger path. It's going to rip the cloth, right? Well, the same thing with the jacket of insulation. It's going to damage the insulation and make a bigger short circuit hole, as it were. It's not a hole, or is it? Maybe it is. But anyway, you see what I'm saying? And that instantaneous leak is going to be a lot of water very quickly, and that can be sensed and turned off in a very short period of time. Very short period of time. So in a way, a short circuit is less dangerous because it's going to be a big current flow, but it's going to happen for a very short period of time. Okay? Overload currents are generally relatively low because it's like a lot of water is flowing and it's just a little more than we're expecting. And it's going to wear parts down in water systems. Kind of not the same thing, but in motors, it makes things start, well, we won't get into that right now. Okay, conductor protection. Overcurrent protection devices allow for overloads for short circuit period for short periods of time. Inrush currents are starting loads. The starting load is an inrush current. We need to talk about motor inductive, the X sub L, right? It's a magnetic field. We've talked about this, and sometimes it takes a little bit of time to build up that magnetic field, right? We're going to see in the lab sometime soon that sometimes it takes almost 2 seconds for that magnetic field to build up because it creates counter EMF, right? Counter voltage. It creates something similar to resistance. And so when you first start a motor, what is the resistance to current flow? Just the DC resistance, which might be 6 to 8 times what it will be after that magnetic field builds up. But we need to let it do that, right? It does. It's got to be able to do that, flow that 6 to 8 times current. Is that similar to a short circuit? No, a short circuit is going to be much more than 6 to 8 times the current flow. It's going to be 10, 20, 100 times more than the normal current flow. You see what I'm saying? Okay, so overload, in the inrush current, once again, when it first starts, it's a very high current, and it ramps down to the full load amperage in a second or two. But during that second or two, we've got to allow the current to flow in a high current situation for a short period of time. Okay? Overload protection for most devices is an inverse time type. In other words, the higher the current, the less time that will allow that inrush to happen. Like 6 to 8 times, an inverse time device, like an inverse time circuit breaker or a time delay fuse, is going to allow 8, 9, 10 times as much current to flow in for about a second or two, right? Not much more. But if that goes on for very long, it's going to heat and trip. Okay? And conversely, if the overload is very slight, an inverse time circuit, how long will it take to trip a 20 amp circuit breaker at 25 amps? Somebody take a wild guess. Would anybody believe me if I told you about 3 hours? Because the overload is only a small percentage, right? It's 20%. And it might be 3 hours. It might not be. It might be only an hour and a half. It might be an hour. It might be a half an hour. But it's going to be a long period of time. Can you see the exponential curve happening here? So it's a great big current, very little time. Little bit of overload, big time. It's an exponential curve. Okay, inverse time means an inverse exponential curve. Okay, so more current, less time. That's kind of a good simplification of it. The more current, the less time it'll allow it to happen. It'll hold 2% of the rating for 5 minutes. 200% for 5 minutes. 20 amp breaker. What's 202 times 20 is 40. It'll hold 40 amps on a 20 amp breaker for up to 5 minutes. Now nothing is manufactured the same as the next one, right? Some will hold it for 5 minutes. Some will hold for 6 minutes. Some will hold for 4 minutes. You see what I'm saying? They're not exact. They're not precise. Just like your timers. Why do we do trial and error testing on timers? Because none of them are exactly the same, even though the exact same type, like pneumatic time delay. A pneumatic time delay might be set at 5 minutes and time out for 5 minutes and a second. Some will time out, 10 seconds less than 5 minutes. You've got to do trial and error. Well, the same thing is true of breakers and fuses. They're going to be a little bit different every time. Okay, 120% of the rating for up to 1 hour. Remember I said 20 amps. What's 20% of 20? Oh, it's 24 amps. I exaggerated. Sorry. So 24 amps, it'll hold for about an hour. Okay, think about that. How long can your body take 24 amps? Your body can't take that, but about a couple of seconds. And then really bad things are going to start happening to you. Okay, conductor protection. As opposed to overload trip characteristics, overcurrent and ground fault protection falls into an instantaneous range of a fuse or breaker. Often the trip occurs at 0.01 seconds or faster in most modern devices. In other words, if it's instant trip, circuit breaker, or fuse, it's going to happen very, very quickly. And that's why, if we're using an instant trip circuit breaker on motor overload protection, or to protect the conductors, and I don't even use any of these terms, and you're going to stop using these terms. You're going to use branch circuit protection for fuses and breakers. Write that down. Branch circuit protection. We're going to use the term branch circuit protection for fuses and breakers when we're doing a motor block calculation. Okay? And an instant trip breaker or fuse trips in 0.01 seconds. That's 10 milliseconds, 10 thousandths of a second. That's very quickly, right? And because of that, that means if we need to let the motor current inrush happen for longer than 10 milliseconds, instant trip is not going to work, is it? So generally speaking, you'll only see, and this is a piece of information you need to write down also, you'll only see instant trip circuit breakers in two places: combination motor starters, and motor control centers. Those are used a lot to control motors, but that's generally speaking the only place you're going to see them. In other words, a factory-built setup. Okay? You generally won't do that because you want this thing to work the first time, right? Unless you know what motor's going in there, don't use an instant trip circuit breaker or fuse. Combination motor starter. Okay. Instant trip generally begins around 6 times the overload trip rating. Why would it be 6 times overload rating? Because we need to allow 6 times the full load amperage to get the motor started, right? Okay, a 20 amp fuse or breaker will trip instantly at currents of around 120 amps in 1.01 seconds, 10 milliseconds. At 120 amps, a 20 amp circuit breaker will trip in a very almost instantaneous time. Okay, now this is what we're looking at. This is the beginning of our motor block information. We're looking at an auxiliary gutter here, and we're looking at 3 fused disconnects, sometimes known as a safety switch, an EXO, or a couple other names. And here we have tap conductors. You see how these come up here, and the black feeder goes into all 3 disconnects. You see that? And it's not connected to any incoming power yet, is it? So notice that the 3 red circuits, so these are all 3 single phase motor starters or disconnects, right? And we have a black and a red feeding each one. We have the neutral here. So if we were feeding this with single phase power, we would come into this auxiliary gutter and feed these 3 taps with power from the distribution panel. And you'll notice there is no fuse between these hot taps and the fuse disconnect. Generally, they're fairly short. And matter of fact, there's a rule about how short those have to be. Can a branch circuit be tapped? 240.21a sends us to 210.19 and 210.20. Sometimes is usually the answer in any code question, not yes or no. It's like asking a question in law. Can you drive 70 miles an hour? No, most of the time. In other words, sometimes, right? If you go up on the highways outside of the city, there are highways where it's posted 70, right? Right. So generally speaking, no, because the state limit is 65. There's a state rule that says the speed limit is 65 unless otherwise posted. Well, the law in the traffic is fairly simple compared to the NEC, the National Electrical Code. Almost any question you ask about the NEC, the answer is going to be, well, maybe, comma, sometimes. So generally the answer is no, but there are conditions where the answer is yes, and that's what we're going to be talking about today. Let's go down a little bit. Now, our favorite part, 240.21b addresses feeder taps. There are several conditions with different requirements in B1 through B5. Write that down. 240.21b, 1 through B5. Part C is used for transformers, secondary conductors, which is also going to become important to you. So write down 240.21c also. Very important clarification in 240.21b is that 240.4b shall not be permitted for tap conductors. What are they talking about? If using any of the tap rules under 240.21b, the next higher device cannot be used, which isn't always true either. What is 240.21? What does 240.21b and 240.4b say exactly? We need to look that up. We're going to have a 10-foot tap rule. 10-foot tap rule says several things. 240.21b11 says the maximum length of conductor cannot exceed 10 feet. The conductor, not the conduit. So can you have a 10-foot conductor? I mean a 10-foot conduit? No, you can't. If you have 10 feet of conduit, how are you going to get 10 feet of wire to get into, you saw the diagram of the disconnect? You're going to need 6 or 8 inches inside there. You're going to need 6 or 8 inches inside the motor, right? And the conductor, the wire, can only be 10 feet to be under the 10-foot tap rule. 10 feet, not 11 feet 7 inches, not 10 feet 01 inches, not 10 feet and a quarter inch. 10 feet or less. Otherwise, it falls under a different rule. Then, the wire has to be sufficient for the load to be served. The wire cannot be less than the rating of the device supplied by the tap conductor. What does that mean? Not less than the rating of the device supplied by the tap conductor. Well, we'll find that out in the code book a little later. Not less than the rating of the overcurrent protection device at the termination of the tap conductors. Okay, 10-foot maximum length rule. The tap conductor cannot extend beyond the enclosure it supplies. Panel board, switchboard, disconnecting means. Our main focus is going to be a disconnecting means going to a motor. Okay, 240.21b13 requires that tap conductors be enclosed in a raceway. Does that mean they can be on a Romex cable? No. Does that mean they can be, I can't think of any other open methods, but anyway, they've got to be in a raceway. Is seal tight a raceway? Flexible seal tight. Rubber coated flex, basically. Yes, it is. That's a raceway. Okay. 240.21b14 for field installations, the ampacity cannot be less than 1/10 of the rating of the overcurrent protection device on the feeder. What are they talking about? On the feeder. Well, we'll come back to that if we're not sure. Oh, there we go. NM, non-metallic. MC and AC cable can be used as tap conductors. No, they may not. Okay. Length of the conductor. The tap conductors have the ampacity of at least 1/3. Oh, we've jumped over the 25-foot tap rule. Sorry. Okay, we want to finish this up. 1/10. What are they talking about? 1/10 of something. Not sure. Okay, we'll come back to that. Let's go to the 25-foot tap rule. So if it's over 10 feet but less than 25 feet, we can use the 25-foot tap rule. Okay, and again, we're talking about the length of the conductor. Tap conductors have an ampacity of at least 1/3 of the overcurrent protection device of the tapped conductor. Okay, they terminate in a single breaker or set of fuses that limit the load to the ampacity of the conductor. They are protected from physical damage by a raceway or other approved means. And there's actually a couple of rules here we have. This is for transformers. We're going to leave this up long enough for you to read it as you're watching it at home later. I wonder what this right here is. Let's see if we can get this out of the way. Okay. This is where we have a feeder primary plus secondary not over 25 feet away. What they're talking about is this thing out here. Transformers are a little bit different. We don't need to work on this just yet, but we are going to work on this later. Okay, as I said, we're going to work on motor blocks a great deal, and at some point we'll start looking at supplying the motor block system with a transformer set where we're kicking the voltage down or up for the equipment that we actually have. It will happen where you will have one voltage at the distribution panel and they're bringing you in used equipment to hook up. That's all one voltage and it's not the same as the supply. So you've got to use a transformer to change that, because voltage is one of the things you can change, right? Okay, so we're going to set up a transformer later. We'll talk about this a lot. So make sure you read these slides now, because this is going to come up again and you'll be able to look it up again later when we need to use this. Okay, taps over 25 foot long. High bay manufactured walls of the building must be at least 35 feet high. Qualified persons service the system. The tap conductors are not over 25 feet long horizontally and not over 100 feet total. And ampacity not more than 1/3 the feeder overcurrent protection device. Terminating a single breaker or set of fuses. Protected by from physical damage. Tap conductors contain no splices. And minimum size is 6 or larger. Once again, I almost never talk about aluminum, but there you have the number 4 aluminum. Tap conductors do not penetrate walls, floors, or ceilings. The tap is made at least 30 feet from the floor. That's kind of mysterious stuff. Don't worry about it. We're not going to be using this rule. This has less to do with what we're going to be talking about than the other stuff in this slideshow. Outside taps, really not part of what we're going to talk about in the next couple of weeks. So you can look this over. It's good code knowledge, but not most of our stuff is going to be involved with outside taps. Okay. And for more information, you can always go to www.nema.org, nema.org, and you'll find articles about Joe that wrote this PowerPoint slide. And you can ask questions on this website, by the way, and they're answered by engineering experts in the field. Actually, they're not so much engineers as electricians who become engineers and really know what they're talking about. And that is all there is to it. And here is that association I'm a member of, International Association of Electrical Inspectors, IAEI, and it's really hard to keep those letters in order sometimes without sounding like McDonald. And that is that slideshow, so you can now watch this again and again. And actually, I think we're going to pause while I get a blank slide so I can make some drawings. All right, let's talk about a couple of, or at least one concrete example of these two rules. Now, you'll notice that we have a 500 amp overcurrent protection device feeding our feeder circuit. This is our feeder circuit over here. This conduit with wires in it that's in blue over here, that's our feeder conduit and our feeder wires, okay? Now, we're going to talk about one more rule before before we go find it in the code book, but we'll talk about that in a minute. Now, what I wanted to point out first is if we have a 20 amp breaker or a 20 amp fuse in these, now let's assume these are all time delay, dual element time delay fuses in disconnects. And this is a 20 amp, 40 amp, 60 amp, and 100 amp. Now, that rule that it gave you said 10% for the overcurrent protection device. Do you think they're talking about this overcurrent protection device right here, the 20 amp? No, they are not. They are talking about this overcurrent protection device right here. Okay? Now, do you think they'd be talking about the ampacity of these wires right here? The feeders? No, that's not what they're talking about either. They're talking about the ampacity of these wires right here called tap conductors, and they're related to the ampacity of the overcurrent protection device. All right? Now, that means that these wires have a minimum ampacity if they're under the 10-foot tap rule, sorry. If they're under the 10-foot tap rule, they must be at least 50 amps. 10% of 500, 50 amps. Right? So even though 20 amp wire, 20 amp circuit only needs a number 14 or a number 12, something like that, depending on what kind of wire, this wire is going to have to be able to withstand 50 amps. So we can't use 20 amp wire, we've got to use 50 amp wire. Okay? You see what I'm saying? That's our tap rule minimum. Now, occasionally, we'll see that in a minute, occasionally the load will be larger than the tap rule minimum. And what do we go with? Go big or stay home, right? We're going to go with a bigger one. Whenever the tap rule minimum is smaller than the actual load, we go with the load ampacity. Everybody clear on that? Anybody got a question about that? Okay, you're going to get tripped up on that in the future, trust me, so make sure that you get this clear in your head. Whenever there's a tap rule minimum ampacity and the load is larger, we would go with a load ampacity for the tap conductor. Okay, now let's look over here. We've got a 100 amp load, possibly. We've got 100 amp fuses in here anyway. Can we go with a 50 amp wire? Depends on the load. If the load is close to 100 amps, let's say it's an 80 amp load. The load is 80 amps, not the fuses. I mean, the fuses are in a 100 amp disconnect. We can put an 80 amp fuse in it, right? Or we might need to put a 100 amp fuse on it and use 100 amp wire for an 80 amp load because, well, we'll get into that later. That's next week. But anyway, if our load is 80 amps on this circuit here and our tap rule minimum is only 50 amps, then we have to go with the 80 amps. We got to do that. We got to have tap conductors that will carry 80 amps if that's our minimum load. Actually, we would have to carry 125% more than our actual load. So if our load was 80 amps, then we'd have to have 100 amp wire there. Is 125% of 80 100? Or is it more? Might be. That's not really too important. Now let's look at the 25-foot tap rule. Now our two center starters here, or disconnects I should say, are 40 amp and 60 amp, right? But they're 12 feet away. They're both not very clearly written. We're saying that they're 12 feet. That means they're not under the 10-foot tap rule. If it's 10 feet and 1 inch of conduit, they're under the 25-foot tap rule. Okay, 25-foot tap rule says 1/3. What is 1/3 of 500 amps? 1/3 of 1,000 amps would be 333. So half of 333, is that it? Maybe? How much is it? 166.67 amps. Let's call it not 166.67. Let's call that 167 amps. Next higher amp, right? So that means that the wires that go to these disconnects, even though the load is less than 40 amps and less than 60 amps. In both cases, we're going to have to take wire to those that will carry at least 167 amps. And that's the 25-foot tap rule. Everybody clear on that? Anybody not clear on that? Okay, so this is clear as it gets, right? Nice simple rule. Now what if, let's just say that this is not a 60 amp load. Let's say this is a 200 amp load. Let's get rid of this disconnect right here, and we're going to put in one that draws 200 amps, or it draws 160 amps, 160 amp load. (160 amps, 167 amps). We've got to carry 125% of this, so we're going to have a 200 amp wire, not a 167 amp wire. The load will define this wire size when the load is larger than the top wire minimum conductor. Okay? We're clear on this. Because you're going to be tested on this about 100 times between now and the end of the semester. Okay, maybe just 10 or 12 times. Okay, maybe just 8, 9, I don't know. All right, so there we have, I didn't need all those slides at all, did I? Okay, well that's all right. So that's what I want to point out. There's a concrete example of the tap rule conductors, and we have total clarity on this. I'm so glad.